basically we have 1 hour left. We have 1 hour left, and I will quickly, I don't know, I think I can't manage to show you all the files, so I will quickly run over the presentation and show you what's where, and then maybe we can do one other script to, I don't know, that I can explain you a bit of the concepts. So I prepared you a second way to download the data. So far we just used the GUI. So there's also a way to access the data space catalog or the data space satellite data using the OpenAI API. It basically dataspace, it has some collections, so it accesses some of the collections. Collections are basically collections of single satellite data. You have to check what kind of data is in there, but still there are some collections. And you have processes, these can be user-defined, or some of them are already included in these processes thing. And then you can basically, so you can access this API using R, Python, and JavaScript. So here's a focus on R. And I actually prepared you a script that downloads the data we downloaded before for exactly the same day. What we get would be not like the whole tile, but this time we download only the data for the IOI. So this does not necessitate to crop the data anymore afterwards. So that's basically easier handling. I won't go to the script because it's basically the same stuff we did before, just it's there. I try to comment every line, so I don't know, if you want to check it out. Yeah, so the second part, or the third part of my presentation was on raster manipulation. I just give you a quick overview what that is. So basically everything is raster manipulation, also resampling we did before, or cropping, or anything reprojecting, it's all raster manipulation. But what I mean with this is that you create some advanced, or that you use some advanced processes to create new information from the raster layers you have already. You can then do that in different ways. So you can generate higher order or higher level information layers based on vector data. You can generate this based on spatial filtering, and you can also use band ratio. So I will just quickly explain the concepts. Here you see a raster layer, or a blueprint of a raster layer. And here you see, like, let's imagine you have building footprints from cadastral data in vector format. So higher order information that you could calculate from that would be, for instance, the count of buildings you have per pixel. So I just added some numbers to say. So you would have, I don't know, a number if there was a building inside, or you would have 0 if there was no building inside, and that would be your new raster layer. You could also calculate the building density. And you could also calculate, for instance, the distance to the nearest built-up pixel, which is also sometimes interesting for you probably to, I don't know, identify if there's something close by to your species. So the second way to do raster manipulation is using spatial filtering. And I'll quickly explain that concept. So let's assume this is a single pixel. So what you see there, it's basically a vegetation pixel. However, the context of this pixel is clearly in an urban environment. So if you would consider multiple pixels and not just that one, you would see, okay, it's an urban area. And that's basically what spatial filtering does. It modifies value of a raster, of single cell values of a raster, using informations from the pixels of the neighboring areas. And that can be usual, or this is usually done using so-called filter matrices or kernels. These are matrices of often a square matrix with an odd number of cells, and they are applied in a kind of moving window approach on your raster. And what you do is then you calculate a new value for the middle cell or the central cell of your moving window and apply it or give it into a new raster. In this case, it's a really simple example. It's the mean of all the values around the moving window. Yeah, there are different examples of higher level information layers you can create using this spatial filtering. For instance, you can generate smooth rasters. so that you reduce the detail. So basically, coming back to the example I gave you before, so you have that urban area with that small park in the middle. So you would probably smooth out the park and just get the information that this pixel is located in an urban area. However, you could also generate or detect edges, so enhance the detail. So you would highlight the boundaries between objects. It's something you could use for segmentation. Segmentation not in the species context, but for instance, if you would have an agricultural area with different plots that are somehow different in your satellite image, you could get the edges of these plots. I mean, it's not working that properly and super nice. You have to try, but that would be an application scenario. Yeah, the specific function or smoothing or whether like this image or this filter matrix is doing smoothing or X detection is depending on the filter itself and on the values in that kernel. So here it's like really simple 1, 1, 1, but usually you have different combinations of values in that filter matrix, and you multiply them with the values in your image, and then you can do some calculations. Yeah. And the third layer information you can get from using raster manipulation is using band ratios. So basically, you combine the information from different bands arithmetically. One way to do so is this band ratio, or the simplest form is you basically have two image layers and you divide the pixel value of one image value from the other. So you do it pixel by pixel and every value gets divided by the other. So the idea behind is that objects and materials on Earth show characteristic reflectance patterns, so spectral signatures in the spectral bands. And by dividing the signatures of one band from another, you can enhance the difference of materials and objects spectrally. And this helps to highlight you specific features. And for instance, it also helps you to reduce effects of the atmosphere. So there are a multitude of formulas that can be applied to do these band ratios in different application domains. So here just a few examples. The first example is the normalized difference water index. So you first, I don't know what bands that are, so you first band 3, I assume it is some band. I don't know, I really don't know what band. So you first calculate band 3 minus band 4, and then you divide it by band 3 plus 4. And what you see here, it highlights basically water areas. So the water areas appear bright. So here is a small, I don't know what it is, a pond or a small lake you see here. And the other areas are not water, so it helps you to detect water. The second index is the most common index. I will explain the concept of that index later. Or in the next slide is basically the NDVI. And the third band ratio combination is like, it's 3 different band ratio combinations you see here, and they are plotted together. So these ratios are plotted together like we did before for the RGB, but this time using these band ratios, and it's for highlighting iron. So basically in this case, it's a small spot of iron somewhere there that pops up, I don't know, brightly. Just to give you an idea what you can do with this. Yeah, the most popular example everyone knows is probably the vegetation, for vegetation indices, normalized difference vegetation index. I just want to give you an idea what it does, also to better grasp the concept why we are using these ratios. So basically, this is a typical spectral profile of healthy and stressed vegetation. So healthy vegetation in dark green and the stressed one in bright green, and you also have asphalt. So the idea is that healthy plants, what we know, absorb high amounts of blue and red light. So that's what we see here. And reflect a lot of radiation in the near spectrum. So basically, this is used, I think, for photosynthesis, and this is due to the high chlorophyll content of the plants.
Das Mikrofon kann so stehen. Okay. Vielleicht ein T-Shirt oder so.
So.
Ein T-Shirt? Ja, das wäre
Okay.
perfekt, danke.
Okay, so stress vegetation or no, senescent plants reflect more blue and red light. You see, yeah, you see it there, and reflect less of the near radiation. So basically, NEVI uses these kind of different reflection and absorption properties of stress in healthy plants. So that's why you calculate it as near minus red divided by near plus red. And NEVI takes the value range when you calculate that between -1 to 1. So basically, values that are larger than 1 are typically associated with vegetation. So here I don't know, took some values that are somehow from that spectral profile. So for the healthy plant, in this case, you get a value of 0.91, so it's really high, so it indicates it's a healthy plant or it's like full cover. And for the stress plant, you see it's still above 1, but above 0, but still it's, oh no, that's wrong. It's basically values. Sorry, it's 0. I correct that later. But anyway, it's still larger than 0, but lower than the healthy plant. And values around 0 are usually an indication for non-vegetative materials, such as bare soils, concrete, or snow. And as you can see here, I calculated the NEVI for the asphalt, and you get a really low value that's close to 0. And the last part, I don't have an example here in that plot, but you would get negative NEVI values, not like super negative, but I don't know, a bit negative when you would calculate NEVI over water. Okay, so I have a script prepared where we basically go through these 3 different raster manipulation things. I would say, I don't know, I can quickly give you an overview of the rest of the presentation. Maybe here. So basically, I would go into raster manipulation because I think this is most interesting for you guys, but I also prepared like how we can use all that information from the manipulated raster and from the stack we created in the first script or in the second script to do a classification and then to do an accuracy assessment, model training, etc. And I also, the last part I prepared is on vegetation phenology. So basically, that's when you look at NEVI multi-temporally, as we do here. So this is like covered, this would be a NEVI profile of a plant for 1 year, let's say, or of 1 pixel for 1 year. And you see that NEVI usually takes kind of a form like you have low values in the early growing season, you have high values in the maturity season, and then the values go down again during senescence. So and that's basically information that we can use to derive some phenological parameters like start of season, high season, the length of a growing season, and stuff like that. So and what you usually do in that scenarios is that you fit a kind of vegetation index curve, because I said before, I mean, we may have every 16 days, like from our sensor defined every 16 days a measurement. However, like this will probably not be the real case. So usually what you want to derive here is you want to interpolate based on the values you have here, a continuous profile so that you would have a continuous value every day. And you can then use these profiles, as I said before, to derive these different parameters. There are different methods. So I don't know, I prepared a script for all of them. So I tried, it's also explained in my presentation. Also, I tried to comment each line in the code so that it should be clear. The data is in the folder, so you should be easily able, I checked yesterday also with the new R version, so you should be easily able to do this. And I will be here next week, so if anyone is particularly interested in that and we cannot cover it today, we can, I don't know, discuss it in small groups or one-on-one if you have, if you are interested. So I would now go to one script, so let's try raster manipulation. 030. And I would quickly go through it with you. Okay. Basically, the content of the script is to calculate new raster layers to obtain some spatial information, as I said before. So we will calculate a new raster layer. This presentation mode. Sorry. So we will calculate 3 layers. So we will calculate a new raster layer based on vector data. In this case, I chose to do it with distance to streets. We calculate a new raster layer based on aggregated information from multiple pixels, so this spatial filtering. We will do an edge and a smooth example, and we calculate a new raster from different as layers, so we will basically use the band ratios, the NDVI. The libraries we need are Terra, SF, RS Toolbox, and ggplot. I hope the links do now work for you. So in the first example, we focus on a new raster layer based on vector data. So basically, the first thing we need to do, we need to have a a vector layer that somehow contains streets. So I downloaded this data, as I said here, from Overpass Turbo EU. It's the version or the web interface that allows you to quickly download OpenStreetMap data for some extent. OpenStreetMap basically is an open community thing where people can basically digitize features on Earth, and that's a good way to go to get access to vector data. So then we load the raster data or the cropped raster stack we have created in the last script, and now I just plot quickly the raster layer on top. Well, first the raster layer and on top the streets layer, so that you get an idea. So basically, these are all primary, secondary, and tertiary roads that you can find here in the surroundings of where we are currently. So calculating distance to streets. So in the Terra functionality, so what we have done now, we have loaded the streets layer as an SF object. In Terra, it's always good to convert it to the Terra. So Terra also has internally a format for vector data that's vect. So it's good if you use the Terra functions with some vector data to convert your data first into that format, in that SPATVEC format. That's what we do here. And then we have the distance function. Takes time to compute. So I said that I just explain quickly what it does. So here we have the Sentinel-2 layer. Here we have our streets vector layer, and we want to compute the distance. So it's the nearest distance from a pixel to the closest street. So let's not calculate that. I will quickly load it and give you a plot of what it is doing. So basically what you see here, here you see the distance value in meters from the streets, and you see the darker spots are closer to the streets than the lighter spots, just to give you an idea. Okay, and the second branch we are focusing on is to calculate new raster layers based on spatial filtering. I downloaded another data set, the global human satellite data layer. It's basically also, it gives you an information, or it has a 100 times 100 meter spatial resolution. And it gives you an idea about, I think I plotted, then it's easier to explain. It gives you the density. This is the density of built-up areas in the environment we are focusing on. I resampled it already to 10 meters so that it fits with our data. But basically, high values are like high built-up concentration, and low values are low built-up concentrations. So, and the first filter operation we will do is edge detection, and a common edge detection filter is the Sobel operator. So in this example, I used a 9x9 Sobel operator. So I just created, quickly. So the Sobel operator you create in 2 directions. Let me quickly show you. So this is like the moving window I explained earlier, but earlier we had just ones in it, so like ones, but this time we have negative values and positive values. And the sum of this filter in total sums up to 0. So what you do is you multiply these whole values with your raster values on the ground, and then you sum them up in this, so all the values you get in this thing. And if there are differences between the pixels on the bottom and on the top, you would get, I don't know, a value that's larger than 0, because these are, I don't know, if you have the same values here and the same values here, these are negative, these are positive, so they would sum up. If you have an increase, so a different value range on the bottom or on the top, you would get some value that's either below or above 0. So that's just, it brings out some, the edges. You also have the transposed version, because like here you, with the first filter, you look in edges in y direction, so like this, and here you look in changes in the x direction. So the way to apply that filter is basically also implemented in Terra. It's the focal function. So here you have to give, like first you have to give them the layer you want to apply this filter to, which in our case is the global human satellite layer. And here you then give the sober operator as a moving window, or the weights function, or however it is called. I think you can just run it because it's quite quickly. Yeah, and now we can plot. So you can see here the differences are popping out. So basically that's mostly the differences from, I don't know, mostly urban areas to outside areas. So it gives you some edges. Well, the second one looks similar, but in a different direction. So what you then do, because you don't want to have the negative or positive values, but you just want to have like a value between 0 and whatever, to pop out the edges. So you square root transform the edges the edges x and the edges y layer. And then you basically get the final edge layer. It looks a bit like this. And as I mentioned before, so this may not be the most optimal layer for edge detection. No, that's wrong. I'm really sorry. That's not that was the original GHS layer, and that's the edges layer. So basically, it gives you it highlights you the outlines of these blobs you had there of build-up areas, and that's something you can do. For instance, we are like also to bring out like the difference between, or the outline between a larger water body and some other area around it. Okay, and the second stuff you can do, or the second application area you can do with these spatial filters is using it to smooth your data. So for this you you have the function focal mat. There you also have to include your data set. Then you have to create some type of matrix. In this case, I created a rectangle, or it's not a rectangle, it's basically a square. And this gives you the radius of that rectangle. So basically from the midpoint to the outer range. Yeah, so let's quickly create that, and I plot it. So it's a bit big, but anyway, you now have where is it? A 59 times 59 square matrix, and in every pixel there's a value that is 1/5, that's basically 1 divided by 59. So if you would sum up all of these, they would, other than in the edge detection case, sum up to 1. So I also wrote some explanation here. So then you can apply this focal matrix. to your data. Again, in this case, you you put the matrix here, FOGMAT. We use the same data set as we did before, the global human satellite layer, and I use the sum. So basically what we didn't do before is specify any function, but you can also specify function. In this case, it's the sum of these. So the matrix is multiplied with the image, and then you build the sum. So it's basically the mean of one pixel, or no, it's the mean of all pixels included in this matrix. Then you save it to drive. I didn't run it, but here, so maybe plot again this one, the original image, and then we load the smoothed one. And we plot the smooth image, so you see it blurs out a bit. And if you look closer, you lose the spatial detail compared to the original layer. For instance, here you still have that, that hole that gets smoothed away when you use this smoothing filter matrix. I also applied one smoothing filter with a larger radius. And that's what I'm loading here. And I also plotted for comparison, so it gets even more blurred out. So, yeah.
Sorry, I'm a bit lost. Why would we want to smooth something that is like a lot more clear? I just got a bit lost. Why would we want to smooth something that is a lot more defined?
Yeah.
In this case?
For instance, if you want to annotate your species with this data, I would imagine I had that example with the urban area, and there you have, like, let's say, a park or something. So if you would annotate that species with that park, it would indicate that your species is in, I don't know, somewhere in a vegetated area, but in reality, it's in a city area. So what you do here, you smooth the data, so it basically reduces the fine detail, but increases the weight of the larger areas or larger surroundings. So in this case, you would say, okay, before there was this hole, that was maybe the park, and now we know, okay, it's in an urban area actually.
So to generalize it.
To generalize, okay. And to get the information. And you also use it after classification, because if you do an image classification, for instance, you get that pixels that are urban and vegetation, and then you can, I don't know, bring out the big blobs of the surrounding areas that are the classes of the surrounding areas, or the majority classes of the surrounding areas.
Okay.
Oh.
All right.
Okay, and the last part I prepared is to calculate the NDVI. We again use the NDVI. Here's the function, and the two bands that are relevant. It's the near band, which is band 08, and the red band, which is band 04. Let us quickly check the names. The names are a bit strange, because always when you save the data, maybe that's also something I should mention, always when you save the data on the drive and reload it again, you will still have, so the band names that we assigned earlier get lost. So what you would need to do, I mean, at least if you're using a GeoTIFF, to assign band names that somehow make sense for you. I mean, you could also name them green, red, whatever near. So I just chose the original band names. So here I have a vector with the band names, and with names basically, with this names function. So with this name function around this, I can assign the band names. So now we have the band names more clearly, so that they can be used in the calculation. So you can calculate NDVI differently. I mean, there are different versions. So here you just calculate it basically using indexing. So you take the near band, you index the near band, subtract it, or you subtract the red band from the near band, then you divide it, and so on and so forth. So basically you just do the operations, indexing the bands. Another way you can do it is using the Terra app function. basically it takes a layer, then you have to implement a function, also querying the layers you want to use in that function, and then providing that function in that app environment. And then it calculates you basically the NDVI as well. However, the app function is a bit slower, or not a bit, like much slower than the other functions. So like going like this or going like in a different way. However, it's sometimes good if you want to implement your own function, and then you can use the app environment because it's easier to implement. And there are also predefined versions how you can calculate your NDVI. One example is giving in the ARIS toolbox. It requires some pre-processing of the data. So first you normalize your image and center it. And then you scale it between 0 and 1. That's what you do here. So you still have the names. And then you have this spectral indices function. So basically what you do, you have the spectral indices, you define a raster layer first, and then you have to assess or assign in your layer the position in your layer to the corresponding band. So for instance, in our layer, band 1 is blue, so we assign it to blue. Band 2 is green, so we assign it to green, and so on and so forth. So you assign all these layers. And then you have these indices function with predefined indices. When you look on the function, let me quickly give you a hint here. So basically here, you have specified all the different functions that can be included somewhere here. So we just calculate the NDVI now, but you can calculate, 100 million indices with this function. But be careful, you cannot calculate all functions, all band ratios with all layers. For instance, here was one, the difference red edge index number 1 would require you to have a red edge band. Okay, we have that now. But for instance, if you use Landsat data, you don't have that red edge band, so you probably, either it throws an error or it throws you an NA, but you cannot calculate it. But a lot of indices are implemented here, so I don't even know what they do, to be honest, but it's just a pointer, so I don't know, maybe you can look what you are interested in. Yeah. So maybe I calculate that quickly. I don't know if I calculate. I will quickly run it. Should go quick because we just calculate one index. And then you can plot the final index. And here you see you get an NDVI with negative values or values like lower than 0 here in the water areas. And you get the different vegetation levels here with super green, like super high vegetation. Probably, I think these are the forested areas and stuff like that. Okay, then you can save it. Yeah. I only have 10 minutes left.
I don't know, until 2:30.
2:30?
Yeah.
Ah, okay. Yeah, maybe we can go for another one. I don't know, maybe we can, so because this was basically the basics of this raster layer calculation, maybe we can go for the phenology. Are you interested in that, or would you, because I think the classification takes too long because there are so many steps, so I don't know. So I would just open the phenology, and I hope we can run a bit through it. So now let me open it from here. Yeah, I discovered early before I came here, I thought I would like to do something on phenology because I like it and I used it. But back then when I used it, I had to do it the hard way because there was no dedicated package to do it. I mean, you could do it, but you needed some proprietary software. So I don't know, fiddled a bit around to do it anyway. So, but now I discovered there is a package, it's named PhenoFit. Here's a paper on it. And it's really cool because it does all the vegetation phenology calculations. It has implemented a lot of curve fitting functions to get you the daily NDVI range. And it has implemented a lot of functions to generally get the different parameters you want and extract the metrics. And it has also implemented some pre-processing that's necessary. So here's the paper. So when you're interested, I would recommend you to look at the paper. And here's also a vignette. And basically, I'm more or less oriented on doing the vignette. But I didn't do it with data that was provided, but I downloaded some of the data. So let's first scroll the different libraries that I needed. Yeah, step one would be to download VI time series with necessary quality layers. So basically, I downloaded now 16-day vegetation index values at 500 meter spatial resolution. So basically, it's do I have the name here? Yeah, Mode 13A1 product. You can download this product via different ways. You can use, for instance, this is a GUI where you can easily download multi-temporal data. It's similarly functioning like the data space environment we looked at earlier, but it's just like a different one. I downloaded the NDVI for our area of interest for 3 years using Google Earth Engine, and I also provided you the code. I don't go to the code because we don't have much time. However, you can find it here, and you can basically just copy paste it into your Google Earth Engine code editor and then run it, and you would get the same. I don't know if you have questions about it. I'm here next week, so we can also talk about that. So basically, the data we have. That's the data we have, yeah. So step 2, add VI time series information to points data. So usually this package doesn't work on the whole raster layer, but you have to extract the signal values for the single pixels. For instance, I don't know, if you have your species, you would extract, the pixel value from the point where you have recorded one location. And I prepared, some samples here. So we load these samples here, we transform them, we give them an ID, and we convert them into the vector package. And I have the list of the different NDVI files. I downloaded data for, I think it's 3 years, 2021 to 2023, 16 days. So I think it's 23 layers for every year when you have the 16-day coverage. So what I do here, I would just run the function. I loop through the points, I guess, if I see it right. I know through the list, and I extract the date and basically the value of the NDVI at that point. Let me show you the result quickly. So basically, what you have after this is you have an ID. The ID is for the point. Maybe that's easier here. So you have the point ID. So here you see ID 1 has 1 layer or 1 date of year at 10, at day of year 10, 1 at 24, and so on and so forth. You have the date, and you have the time. So that's probably some concept that's interesting to explain. Let me quickly go back. Because basically in these time series you get from MODIS, you have 16 days coverage. I mean by definition. So they say we have every 16 days a coverage. However, you won't have, or it's highly unlikely that you would have an image, a MODIS image taken on that day. So usually they take an image from the period before or after that had good quality and assign it gets assigned this date of that regular time series. So in that DF, you have basically both. Or let me show it with this, and it's easier. You would have basically both. Date is the composite date, so it's the date of the 16 days time series, the regular date, and then you would have T, which is the image date, which is actually the date of the image that was taken to fill in that particular spot of the time series. Okay, so let's just quickly plot it. So we focus on one particular point. So I focus on a point with ID 5. So let's just quickly check where it is. Oh no, that was one. So basically we focus on one particular pixel that's located here. And here we plot the time series of the 3 years of the NDVI we've got from the downloaded MODIS data. Zoom it out quickly. So basically you can see, like, this is, I don't know, you can't see the thing, but you have this like going up, going down, going up, going down, going up, going down. So you have roughly 3 growing periods in that data. Okay. So now we are coming to Phenofit. So Phenofit has different ways of doing the stuff. So the first way is, let me quickly check again, initialize ways. So basically they indicate the quality of the measurements. So some of the measurements maybe have been a bit occluded by clouds or by haze or so on. So you assign some quality. That's what you do here. So for instance, you have this, what we added here is this flag. So you know now, okay, this was snow, this was good, this was marginal. So you have these 3 classes. And accordingly, you have the weight. So snow pixels, of course, get a low weight because they are not that useful. You have that marginal pixels that are medium quality that get a weight of 0.5, and good pixels get a weight of 1. So the next, that's basically just 3 functions. I try to go with you to the 3 functions. So we have now this data frame with all these values, and we can now pre-process the input NVVI. So I've just listed up what it does. It checks the input data. It interpolates some values. For instance, if you have missing values in your regular time series, it interpolates this missing value. And it removes spike values. Spike values would be something like, I don't know if this is a spike value, but usually it's some value that lies far off the regular transit of this thing. And it sets weights for an A and Y, so basically it replaces some stuff, yeah.
So it would remove also this.
Yeah.
It would remove also the spikes negative, huh?
Yeah, the negative ones, the positive and the outliers in general, sorry. So let's just quickly run it. So here you just define the time, you define the NDVI, epsilon is our NDVI, you get the weights and the QC flag. So this is number of points per year you should have. These are 23. And here you define the maximum number of gaps allowed to do that interpolation. So in this case, it's 23 divided by 4. And this is some minimum weight that should be assigned for bad points. So what you get here is a list that is now, I don't want to go into detail, so but that is now, it's just the input basically you use now for the further processing. So the second step is the growing season division, and that's actually kind of nice that this is implemented. I will quickly just run the function. The growing season division, or maybe it's easier if I plot it. Yeah. So you have the years displayed here. So this is basically year 2022, 23, and 24, as far as I get it right, yeah. And you usually don't, or it's not often that your growing season just is within a year. So I don't know, in this case, or that you have multiple growing seasons within the year. For instance, if you have grassland gets mown, then you get, I don't know, then the NEVI would drop and then it would regrow until it gets mown again and stuff like this. So you would have multiple peaks within a year. And this basically discriminates you the periods so that you have only 2 minimum values and only 1 maximum values. And what you see here is that the growing season for 2023, if I'm right, only starts some, I don't know, not on the 1st of January, but some is a bit shifted into the middle of the years. So that's really cool, actually. And yeah, this is a coarse curve fitting function. So basically you see the original values you take here. You have them assigned to good, marginal, or these snow points or cloud points. And you run 2 iterations for curve fitting. I don't know, it's just a refinement. The second one is finer than the first one, something like this. Okay, now that we have defined these breaks, I mean, it's explained there. I would say I'm not going into every detail there. I just explain you the basic context. So the last one would be to reconstruct the daily NDVI profile. That's what you do with curve fitting. So basically, maybe going back. Okay, it's not here. Curve fitting, then basically you have here this irregular time series, and now what you do is the daily profile you want to have. So you can use this function. It generates you a fit. And let's also quickly print it or plot it. So this basically gives you the fine fitted curve. So now you have reconstructed a daily NDVI profile for your different years. You have also the rough fitting animation in black. That's basically what we fitted before to define the breakpoints of the growing season. You also have the original values again, and you have some iteration. You can define the number of iterations. And what you have here are different methods used for curve fitting. So there are different ways how you can do the curve fit. And you can define them or you can use few of them. Here we used few. I cannot say what they do. I mean, some work better, some work best. For instance, here you see that sharp edge in Sang that is not there, for instance, when you look at back. I can't really explain you all the different functionalities, but I know they are explained in more detail, not in super detail in that paper. So if you're doing or interested in it, you anyway would need to choose a proper algorithm. So and this is the basic to define the phenological matrix. Maybe I quickly go back to the presentation for that. We prepared the input data, we did the curve fitting, and there are different ways to extract this matrix. I don't know, provided you with 2. So one really simple way is the threshold method. So basically you choose an NEVI threshold, then you throw it over the whole year, and then the first point is the start of the growing season. Remember, we have defined a growing season so that it only contains 1 peak, so that it should work everywhere. And the second point when this threshold is crossed is the end of the growing season. So this is a really simple method. And another method is using the derivative. So basically you calculate the derivative of this curve. And then this first peak here, so it's the rate of increase in that in NEVI until it reaches a peak and it slows down. That's the beginning of the growing season. When the derivative passes 0, so as soon as it becomes negative, is the peak of season, and the last point is when it starts to increase again. It's the end of the growing season. Yeah, maybe so. why is it important to calculate these kind of things? It's basically you can identify some effects of climate change. For instance, shifts in phenological matrix. So, for instance, the beginning of the growing season might be shifted if you look over the last 20 years because it gets warmer or earlier warmer, and then starts earlier to grow. And an example from species-environment relationships are the green wave studies. I provided you some resources there. So basically, they determine the peak of green up and assess if herbivore species adjust their choice of foraging habitats during spring migration to coincide with this peak. And it's basically the derivative method. They name it a bit different. The derivative here is called instantaneous rate of green up, and the peak of green up is the start of the growing season. And then they could assess or act this point or this information to the points of the species and check it. Yeah, so let's quickly, so we have now done that curve fitting, and for the last part, to get the phenological matrix, I mean, if you want to use the threshold method, you just have to define some of these thresholds. And then you get a print, or you can print it here. So here you see the different ways. It's also like maybe also an explanation. So this, we get several plots here for, you see, Zhang, AG, and whatever. So these are basically the different curve fitting mechanisms that were used to do the curve fit. And these are the resulting derived metrics using the threshold methods. In this case, the threshold of 0.5. Let me quickly zoom out. Or, you have different methods to derive these parameters. You have here the initial curve fitting. What's also interesting, I downloaded 3 years. Usually it's also good to download not just the year you're interested in, but the period before and after. Because as you see, the fitting, so you have here a value grading the fit, the quality of the fit is best in the year between these 2 years. So it's usually better to download some more data. And here are, for that particular back curve fitting thing, some different methods to derive these start of season, end of season. Here's the threshold 0.5 version. Here's the derivative versions, and here's some other versions. I don't really know how they work, but they are also documented in the script. So that's basically it. And what is really nice is that this is all implemented really in one package, because I had to do it like with different things, and it's really, really cool. Yeah. Okay. So I think that's it. Let me quickly give you an overview. So I have some more scripts, or had some more scripts that I had prepared but cannot show today, but they are still in this files section, and they are also mentioned in the PowerPoint presentation. So I also try to, for every script, give some explanatory slides so that you can, know or understand what they are used for. I try to comment the code best as possible. I'm not sure if it was really good. But anyway, I'm here next week. I mean, I've said that already, but if you have any questions regarding this stuff or regarding other stuff that comes up or remote sensing stuff, I'm here to help. Yeah. So, thank you very much. Any questions before we switch to the next topic?
The value of the threshold is something that either we find in literature or we know.
I think in literature or thresholds are generally, I don't use thresholds because they are random. I don't know, this 0.5, okay, you would say it would give you the half between the maximum and the minimum. So, yeah, I think just check in the literature. Yeah.
Okay, and play around.
Yeah,
okay.
yeah.
Thank you.